talking about electromechanical energy conversion under two different situations, when the movement is really fast and when the movement is really slow. So in the two cases, we derived the expression for force as in one case it was dou Wf divided by dou x, actually reduction in the field energy, with, I would say, in this particular case the movement was actually slow. So because of which we said I is constant. So we call this as the case corresponding to slow movement. Right? This was the first. Let me try to think. Yeah, yes. So this is actually this. Sorry. Yes. In the first case, we were talking about the field energy. In the slow case, it was the co-energy. Okay. So in the other case, which was corresponding to the reduction in the field energy, because of which we said minus Wf, and of course we said lambda is constant, and we said this is fast movement. Right? And then we just started talking about what is a linear system, and that's where we had stopped the class in the last session. So if we are looking at actually a linear system, what actually we are trying to imply by saying it's a linear system is lambda and I are linearly related. After all, lambda we said as n phi, and which means number of turns anyway is not changing. So the flux and current are linearly related. So if I try to plot the magnetization characteristics, I am trying to say that they are mainly operating in the linear region of operation. So we are going to have lambda and I linearly related. So when they are linearly related, we said already that Wf and Wf dash are one and the same, right? Because we said that essentially the total, total actual area will correspond to lambda times I, which will be actually the rectangle, and then you are going to have the diagonal exactly intersecting, the area into two halves, exact two halves, because of which Wf and Wf dash will turn out to be one and the same in terms of the magnitude. So we are actually looking at, if it is a linear system, we are essentially saying that lambda equal to Li. Already we said lambda is equal to n phi. There is no change in that. But we are also writing n phi equal to Li. So because of which we are going to take actually L as n phi by I, rather than taking it as n into d phi by di, we are taking this as n phi by I. That's what we are taking as the inductance, right? So if I am talking about, say, Wf, we said Wf under static condition, when there is no movement, is I d lambda, right? And Wf dash happens to be lambda di, right? So if I write what is I d lambda, I can write that as lambda divided by L, because I am writing lambda equal to Li multiplied by d lambda. So I am going to get lambda square divided by 2L as the integral. If I want actually what is the overall field energy, this is what I am going to get, which I can write this as Li the whole square. Lambda is Li the whole square. So I can write this as 1 by, that is half multiplied by L square I square divided by L, which is half Li square anyway, which we know as the field energy, right? If I try to look at Wf dash also, I should be able to write this as Li di integral, which will again come out to be half Li square, which is already known. We are just actually reiterating that. That's all we are trying to do. So whether I look at Wf or whether I look at Wf dash, both of them happen to be the same. So if I try to actually look at what is the force, we said as, say, dou Wf dash divided by dou x, but with lambda equal to constant. Right? That's what we said as the force. I equal to constant. Let me look at again and again. We are looking at dou Wf dash is clearly yes. So I is constant. This is slow motion. Fine. So I is constant. So we can say this is essentially half Li square, whether I'm looking at Wf dash or W, it doesn't matter. Wf, it doesn't matter. So dou of this with respect to dou x. So I don't know how exactly the inductance is going to change. After all, the current invariably we assume it as varying only with respect to time. We do not really, look at that varying with respect to the position. So we are essentially going to write this as half I square dou L by dou x, with I being a constant anyway. Right? So we are taking a partial derivative basically of the inductance. Inductance might vary with respect to current as well, because if I reach saturation, the inductance value is going to decrease because the permeability is not a constant. But given I as a constant, we are trying to look at how the inductance varies only with respect to the position alone. And this gives me what is the force. So if you recall what we had done earlier as for Wf per unit volume, we had done this as V square by 2 mu naught. We are basically talking about a similar system what we had conceived earlier. That is, we are actually having basically a system, maybe a translational motion system. We have not migrated to rotational motion. This is translational movement system, and we are talking about this as the moving part. Right? And this as the stationary part, from where I am getting the excitation. Right? This is the current that I am forcing in. At this point, we are basically talking about if I am allowing the movement. At that point, and that too allowing a slow motion. In that case, we are basically talking about how the force is evaluated. The force involved, how it is evaluated for a given value of current. See, actually if you look at the evaluation of L, it will be a continuous function because you are not seeing abrupt movement. It's a slow motion. It is probably starting off from x1 and then it is moving to a portion until x2. So you are looking at air gap gradually decreasing. So you will have a continuous variation in the inductance because you are going to see a continuous variation in the reluctance. That's what we are looking at. Right? So when we are actually looking at, the linear motion, for that we are saying that how the inductance is varying with respect to the position. That's what we are looking at. Right? So if we actually looked at the original value of Wf, whatever we derived before sometime, or we can derive it again, half Li square, that's what we said as the Wf value. This I should be able to write this as half L is after all n square by reluctance. So I'm writing reluctance as REL. so that I don't confuse it with resistance, multiplied by I square. Right? So this is essentially representing half. On the top I am having mmf square. N square I square is mmf divided by the reluctance itself. Right? So mmf I can multiply and divide again by the reluctance. Let me do this so that mmf square divided by reluctance square will give me flux square. Right? And then I can write this reluctance as L divided by mu A. If I am talking about mainly the air gap, let me write this as mu naught A. If I am talking about the energy stored in the air gap. So if I am going to talk about mainly the air gap stored energy, because mu naught is much smaller than mu naught times mu r, I am basically considering this. So this area is actually area of air gap, and this is going to be the length of the air gap, if I am talking about the air gap alone. So I should be able to write this as half B square A square LG, maybe AG square I can say. G is also indicative of whatever is the flux density in the air gap. So divided by mu naught AG. So this AG and this AG get cancelled. So I am going to have AG times LG is actually the volume. So this is what we said as B square by 2 mu naught is the field energy per unit volume. This is what we said earlier also, just reiterating that. That's all. Okay. So if this is the field energy per unit volume, as we just expressed it, if I want the full field energy, I have to multiply that by AG times LG. That's all. Right? Yeah. Because the air gap stored energy happens to be much higher as compared to what is being stored in the core, because the core permeability is quite high as compared to what is going to happen in terms of the air gap. So most of the energy that is going towards magnetizing the entire structure goes into actually magnetizing the air gap, because the air gap is difficult to magnetize. You are going to have higher and higher reluctance. So that's the reason why we are saying we are mainly looking at the air gap. Right? So this actually will be the WF value per unit volume. If I try to now look at what is dou WF by dou X or dou WF dash by dou X, either way, right? Because WF and WF dash are the same, that's what we said. So if I try to look at this, I should do this actually with respect to the distance. So that is essentially the length of the air gap itself. So I should be actually doing this with respect to dou LG, because that is what is the length of the complete magnetic path. Okay. So maybe if I say this is LG, or I should call this as LG by 2 and another LG by 2 here, so that when they add up it becomes LG. That's all. Basically I am looking at what is the length of the air gap. That's it. So this is going to be, again if I say B square by 2 mu naught multiplied by AG multiplied by LG, LG will just be eliminated when I differentiate it. That's all. So this is going to be the force that is produced in the air gap, whose flux density is B and whose area of cross section is AG. Right? So in which case I can say force per unit area will be B square by 2 mu naught. Right? Because area is AG. So if I try to calculate what is the force per unit area, we said first energy stored per unit volume in the form of field energy. That is also B square by 2 mu naught. And if I try to calculate what is the force per unit area as visualized by the areas which are exposed to the air gap, I will again get that to be actually B square by 2 mu naught, right? So we are just making some jugglery so that we are able to arrive at some expressions which are more comprehensible in terms of flux densities. Because finally, you may be given a material whose flux density, the maximum flux density that you can arrive at is so and so. In which case, you would be able to calculate what is probably the maximum force it can develop, right? Provided I pass sufficient current to drive it to maximum flux density, criteria. That's it. So as long as I actually operate with the limitation on the flux density, I also have a limitation in terms of what is the maximum force I will be able to develop for a given material, right? Per unit area. Of course, if I increase the area, I'm going to get definitely more force, right? So let us now, having derived the force expression, all these whatever we talked about was with reference to only a machine which is translational in nature, which is like an actuator. That's it. Nothing better than that. Maybe a relay, maybe an actuator. So we would like to derive a similar thing for a rotating machine, because we are going to deal with rotating machines basically. So let us say I am looking at a rotating machine, right? So in a rotating machine, as I told you, we will have very clearly two members. One will be a stator, the other one will be a rotor. So let me probably take this as the stator again. I'm just taking a C-shaped magnet, right? So let us say this is my stator, and I'm going to have a coil wound around this stator structure which will try to magnetize it, right? So this is the current which I may call that as IS, because it is a stator current. Okay? Now I may have a rotor probably which I mount it here in such a way that it will rotate probably around this. So I'm just having the rotor structure which is going to rotate continuously, maybe in anti-clockwise direction or clockwise direction. It is riveted in the center and it is free to rotate probably around the center. So I am looking at the rotor, and the rotor might also carry a current. It is not singly excited, it is doubly excited. It is excited from both stator as well as rotor. Okay? So maybe I'm going to have one more current passed here, which is actually the rotor current. And both of them are definitely going to interact with each other ultimately to produce the rotational motion. So that means the torque will be in all probability a function of both stator current and rotor current. The question was, why do you say there might be a current in the rotor? There is always a current in the rotor. It is not true. It need not be true, right? For example, I'll give you an example of a stepper motor. Okay? In a stepper motor, I'll just show you crude structure of a stepper motor. You may have something like 8 poles or 6 poles sitting in a stepper motor. I'm just showing these are the poles. Okay? So this gives you at least a practical example of a machine where I have only one side excitation. So this is the stator. It is, imagine it's the cross section and it is a cylindrical machine. So I'm showing essentially this expanding into the paper. Fine. Now I may call this as A dash, B dash, and C dash. So I have 3 pairs of poles. Okay. Now let us say I have the rotor in the form of a plus. Actually, it will not have so much of air gap. I am essentially accentuating the air gap. So you can imagine it as though it is, a little longer than what I have shown. So this is the entire rotor. The rotor does not have any winding in many of the stepper motors. You will not have a winding as a rule in the rotor of a stepper motor. It may be made up of a permanent magnet sometimes, but generally it need not have any winding or even a magnet. So what I may do is, let us say I start off with exciting B and B dash. I will have windings around each of the stator poles. So if I excite B and B dash, the natural tendency of any magnetic system will be to minimize the reluctance. So either this has to come here or this has to go here. So if I may name this as 1, 1 dash and 2, 2 dash, either 2, 2 dash have to align themselves with B, or 1, 1 dash have to align themselves, all the way it has to come towards B and align itself. I will not excite all the 3 pairs of poles simultaneously, never ever. I will only excite B, B dash, then I may excite C, C dash, then I may excite A, A dash. I will do it sequentially. So any system would like to do minimum work. That is true for every mechanism. So obviously it is going to make sure that this to move here will be much simpler rather than this all the way to move towards B, B dash. Because this will be only about 30 degrees or something, whereas that will be 60 degrees movement. Please realize that this is right now in a vertical position and it has to move by 60 degrees, whereas this has to move only by 30 degrees. So in all probability, 2, 2 dash will move by 30 degrees in anti-clockwise direction and align themselves with whatever is the pole that is being excited, which is B, B dash now. Right? No winding is there in the rotor. But this will work only if I have the rotor poles to be attracted because of them being made up of ferromagnetic material. The rotor has to be made up of a ferromagnetic material. I can't have it as any other thing. It has to be attracted because of the electromagnet that has been created in the stator because of the excitation that we have given. The excitation given is now to B and B dash. After giving the excitation to B and B dash, and once the poles are aligned, I can remove the excitation from B and B dash and give it to C and C dash. Then again, whatever is the closest pole, that will try to align itself with C and C dash. So for every pulse what I am giving, I am calling this as a pulse. A and A dash I am giving one pulse. Then B and B dash I am giving another pulse. And C and C dash I am giving the next pulse. All of them are definitely not excited simultaneously. So as I give the pulses one after another, I will see the alignment of rotor poles, whichever is the closest to the excited phase or excited poles in the stator. So generally, in this particular case, we call the movement as the step angle, because for every excitation, it will move by a particular angle called step angle. So in this case, we saw it as about 30 degrees, because 90 degrees actually is the angle between this pole and this pole. Right? Rotor pole is displaced from each other by 90 degrees, whereas the stator poles are displaced from each other by 60 degrees. I have not drawn very well, otherwise you should see the 60 degree clearly. Right? So normally the movement is whatever is the pole pitch of the rotor minus the pole pitch of the stator. Pole pitch of the rotor is 360 degrees divided by 4 because there are 4 poles. And this is 360 degree divided by 6. So I'm going to get 90 minus 60, which is 30 degrees. So for every step, I will get basically 30 degree motion. So if I am going with A, B, C and then A, B, C, I will get anti-clockwise movement. If I am giving rather C, B, A, C, B, A, I will get clockwise movement. Please analyze it and check it out. You will get it that way. If I try to do it with C, B, A, I will get clockwise movement. And if I get give A, B, C for the naming what I have done. For A, B, C, I will get anti-clockwise movement. So there are very much machines available which have only ferromagnetic materials in their rotor, no winding whatsoever. And they are rugged. They are really rugged. You cannot really spoil them very easily. Because there is no question of a winding being thrown out. There is no question of any winding actually, shaking and coming out, or whether it is getting short-circuited. All those things are completely eliminated, because of which the structure is pretty much rugged. They will not get spoiled so easily, these kinds of machines. But stepper motors are available only for smaller ratings, not for very large rating, maybe until 1 kilowatt. That is the normal rating we see. Whereas if you look at synchronous machines, induction machines can easily go up to a couple of megawatts. Synchronous machines can go up till thousands of megawatt. So you can't compare the capacities in terms of what stepper motor can offer vis-a-vis what a synchronous machine can offer. Okay? So we do have, let's say we are going to talk mainly about doubly excited machine in this course, mostly. That's the reason why I took an example with 2 excitations from stator side as well as rotor side. And under a static condition, I should be able to say I d lambda. That is what we called as the field energy. Right? So because of which now I have to consider the field energy corresponding to the stator as well as rotor. So I'm going to say Is d lambda S plus Ir d lambda R. Right? That is the total amount of field energy that I will get. Or I should say this is dWf on the whole. Right? In which case, I have to know first of all what is lambda S and what is lambda R. And lambda S is essentially telling me that d lambda S by dt will be the induced EMF in the stator. Similarly, d lambda R by dt will be the induced EMF in the rotor. So, will there be an induction in the stator if I have a current flowing in the rotor? If the 2 coils are mutually coupled, if one's flux is going to influence the other one, definitely they will be influencing each other in terms of what is the amount of induced EMF. We can't help but have the influence because you are having a ferromagnetic core and the rotor winding is very much in the vicinity of that ferromagnetic core on which the stator is wound and vice versa. So, I can write basically that lambda S is equal to LSSIS, where LSS is its own self-inductance. That is essentially the induced EMF that will be showing up because of its own current. So, we are looking at LSS as its own self-inductance. Plus, I have to write along with this, there should be definitely LSR, which is the mutual inductance between the primary and the secondary, like what we talk in the transformer, or between the stator and the rotor in this particular case. The 2 windings multiplied by IR. This is what is my stator side flux linkage. And as far as the rotor side flux linkage is concerned, I am going to have lambda r equal to LSRIR plus LRRIR. So this LSRIS. Thank you. Yeah. Fine. So both these things are going to be actually corresponding to the stator and rotor flux linkages respectively, and we are assuming a linear system. That's why we are able to put it in a way that it is L times I. That's what we are writing all along, right? So I should be able to write now dWf as Is multiplied by d of LSSIS plus LSRIR, right? And plus I should be able to say IR multiplied by d of LSRIS plus LRRIR, right? So I can write this as Is d of Is multiplied by LSS. I can write like this. And then I can write LSR. I am having Is dir and IR dis. So I should be able to write this as d of Is IR. Right? UdV rule. UdV plus VdU. That's all we are doing. Right? And one more term, what I am going to have is LRR multiplied by IR into DIR. Right? So I am having three terms here. One completely corresponding to the self-inductance of the stator. One completely corresponding to the self-inductance of the rotor, which involves only the rotor current. And the third one, which is corresponding to the stator and rotor current with the mutual inductance between them, the stator and rotor entities, right? So let us try to look at again WF. What we wrote was WF, dWF. Now what I want is full WF. So WF actually should be this entire thing integrated. Right? So I have to integrate this, I have to integrate this, I have to integrate this as well. So if I integrate this, I should say IR DIR. Here I should say IS integral of IS DIS. So I should be able to say clearly the first term will be half LSS IS square, which is the stored energy in the because of the stator winding carrying a current of Is. The second one will be corresponding to the rotor, which will look similar. So this is the rotor self-inductance multiplied by the rotor current itself. And the third one, which does not have a half there, we are going to have essentially whatever is the mutual inductance between the stator and rotor multiplied by Is and IR. LSR. At this instant, we are looking at first of all static condition. We are looking at static condition. Currently what we are looking at is, otherwise I could not have equated ID lambda directly to the field energy. How can I? ID lambda is actually the electrical energy input. All along we said we can equate that to the field energy only if the entire system is static. And the system is static, that's why I can take LSR as a constant. Otherwise it is definitely a function of theta. Very clearly when they are in alignment I will have the maximum inductance. When they are not in alignment I am going to have, at 90 degrees I am going to have minimum inductance. Right? So we will have definitely variation, no doubt. So this is going to be my WF. Now if I try to look at dou WF divided by dou theta, because I have to look at the whole thing with respect to theta. Now, right? This will give me, rather than force, I should call this as now torque, because we are just migrating to the rotational system directly. Right? So in which case, I should have this to be half IS square dLSS by d theta. And I will have half IR square dLRR divided by d theta. And finally, I am going to have IS, IR, because we are talking about this when the current is a constant, because WF and WF dash are the same. So we are looking at when we are deriving the torque, we are assuming current is a constant. So this is going to be dLSR divided by d theta. Right? So these are essentially the three portions of an electrical machine's torque. And these two are due to the self-inductance variation of the stator and rotor respectively. The self-inductance, will it vary or not? It depends upon the structure of the machine. For example, if we had looked at this stepper motor, very clearly if I am trying to look at the inductance of this coil, that is, let us say the coil that is wound around B and B dash, or A and A dash, or C and C dash, when I am going to have a complete alignment, the inductance will be maximum. Even for the coils which are wound around the stator poles, when the rotor is aligned completely with the stator, I am going to have maximum inductance, because minimum reluctance will be there. The air gap path basically will not be followed as much as possible. It will try to, if I try to look at the magnetic field lines under aligned condition, it is going to go like this. This is how the magnetic field lines will be. So please understand that the coil inductance depends upon how much is the air gap that is visualized for a magnetic circuit or magnetic field line. So the magnetic field line actually will pass through really minimum amount of air gap when the stator and rotor poles are aligned. So you are going to have a variation in the stator coil inductance. Even though the rotor is really not having any coil, in this case the self-inductance variation is the one which is actually creating the torque, because the rotor current is not even there. So if I try to look at the expression now what we got, this is due to stator self-inductance variation. And this is due to rotor self-inductance variation. And this is due to mutual. Right? How can you assume LSR to be a constant? So LSR definitely is not a constant. It's very clear from this that dLSR by d theta is the one which is really contributing towards the torque because of the interaction between the stator and rotor currents. If both of them are carrying current, I will definitely have interaction between the stator and rotor currents and their mutual coupling also. That is what is producing the interactive torque finally between stator and rotor, and that happens here. So this is due to the mutual inductance that is coming up between the stator and rotor and the interaction between the stator and rotor currents. So if I may say that these two are due to variation in the reluctance, the self-inductance variation is essentially due to the variation in the reluctance path. So these two are generally known as reluctance torque components. So these are reluctance torque components. So the reluctance torque components will be visualized only if physically the reluctance itself is changing for some reason or the other. If the reluctance is changing for some reason or the other, maybe because of the movement of the rotor which is having protruding structure. You guys understand? It's not a smooth structure. It is having protrusions in the form of poles. But I may have machines where my stator is also cylindrical, my rotor is another concentric circle. Cylinder. Two cylinders inserted inside one another. Both will have a pretty smooth structure if I just look at them, superficially. So I may have definitely some slots and so on and so forth where the windings are inserted, but by and large, if I look at the air gap is completely uniform throughout the circumference. In which case, there is not going to be much variation in the self-inductance at all. Whether I look at the stator or whether I look at the rotor, for any position, I am going to have the air gap to be uniform. So it is not going to differentiate between position A and position B. There is no question of any variation in the air gap and hence in the reluctance. So I will not get any reluctance torque. So this particular component will be equal to 0 if both stator and rotor have cylindrical structure. So if both of them have cylindrical structure, the air gap is uniform. Because the air gap is uniform, I will not see normally any torque produced because of the reluctance variation at all, because there is no reluctance variation, absolutely. Whereas this generally will always be there in most of the machines, provided I excite both stator and rotor. Of course, stepper motor is an exception because I am not really exciting the rotor. So I have only the stator side excitation. So obviously what I have there is only the stator side reluctance torque. I will not have the torque due to rotor side current because rotor side current is 0. And I will not have IR into dLSR by d theta because I am not having IR at all. Right? So whenever a machine is doubly excited, I am going to have for sure the mutual inductance prone torque. Right? Whereas whenever I am going to have a cylindrical machine, I will definitely not have reluctance torque. Right? And whenever I have a singly excited machine, I will have only reluctance torque due to the member which is being excited. For example, if I look at the DC machine, generally it is a cylindrical structure. The stator as well as rotor will have fairly a cylindrical structure. So in which case, I am not going to get these two. The reluctance torques, whatever I am talking about, they will not be present. So only thing that may be present is this. So we call one of the members which carries the current is as the field system. So one of them happens to be the field current. The other one seems to be the armature current. So I'm going to have IF times IA being proportional to the torque. Now I have to look at how exactly LSR varies with respect to theta. Right? So if I actually look at LSR, how it varies with respect to theta, we are slowly migrating into DC machine. That's what we are doing. Okay? So if I have, let us say, this is going to be probably my stator pole. Of course, there will be a small protrusion normally. I may have a north pole here. I may have a south pole here. This will try to encompass as much area as possible. That's how it will be. So I'm going to have stator and rotor probably. This is stator and I am going to have the rotor winding, which is actually in the outer periphery of the rotor, like this. Of course, they will be in the slot. So, if I am saying that I am having basically the magnetic field line, going like this and then completing itself through the yoke region. Yoke I have not shown. The poles cannot be attached to nothing. They have to be attached to the yoke, clearly. So, there will be a yoke region. So, the yoke, through the yoke it returns, the magnetic field line return. So, if I try to look at really what is the kind of, maybe all these things are carrying a dot and all these things are carrying a cross of current. Let's say, arbitrarily I am just taking, right? Because of which I will have probably this magnetic field corresponding to the stator is exactly passing through the rotor and then, completing itself through the yoke. If I look at this, I have to say, normally I am going to have this as, if it is dot and this is cross, I would have had the current, magnetic field line going up. Now maybe I will have the magnetic field line going down in the case of rotor as well, maybe, right? So, if I am having the magnetic field line aligned exactly with that of the stator winding, I am going to say theta probably is equal to 0. But at any point in time, theta is going to continuously change. So, depending upon whether the stator windings and the rotor windings are aligned with each other, I am going to have either theta equal to 0 or theta equal to 90, or they are aligned, misaligned, exactly opposite. I will say theta equal to 180 and so on and so forth. So, if I look at the magnetic, rather mutual inductance, it will be a function of cos theta. When they are aligned, I will have maximum mutual inductance. When they are completely unaligned, then I am going to have minimum mutual inductance. So, I should have basically the mutual inductance as a function of cos theta. This is how it will be in generally in any electrical machine. So, this is going to be the mutual inductance function. So, when I say d LSR by d theta, this will become sin theta basically, because cosine, when I actually differentiate, I am going to get a sine. Forget about the sine minus sin theta or something. Just this is going to be a sine function basically. So, I know that d LSR by d theta is going to be a sine function ultimately what I get. But if I ensure that between these two, that is whatever is the actual displacement between the stator and rotor windings, which is actually theta, if I try to make sure that they are always aligned somehow or the other, right, or they are always at some 90 degrees, I can do this by modifying the structure in some way or the other. So, what we do in a DC machine is to make them exactly at 90 degrees to each other. So, d LSR by d theta, which is actually m times sin theta, theta is always made as 90 degrees by inserting the commutator. That's what we do in a DC machine. The commutator is essentially a DC to AC or AC to DC converter. So, what we do in a DC machine is to make sure that the maximum contribution comes from the mutual inductance between the stator and rotor. And that essentially contributes to, the torque being simply m times, IS and IR. And what is IS? That is actually the field current. What is IR? That is the armature current. So, the torque will come out to be m times IF and IA. That's it. Nothing more than that. So, it becomes a simple scalar expression. IF is also DC, IA is also DC. So I'm able to really look at the whole thing as a simple scalar equation. So that is the major advantage of a DC machine. Whereas in AC machines, you're always going to have a phase angle for the current with respect to the voltage, and you don't even know whether the rotor current and stator currents will have the same phase angle. There is no guarantee. So I just don't know really how the fluxes are displayed.